Hi, this is Betsy Dobbs-McAuliffe again, and we're going to continue with Chapter 12, Transport Across Cell Membranes. And we're beginning with the video that reviews transport of glucose across the gut epithelial cell.
One important task for cells lining the lumen of the gut is the uptake of glucose produced by digestion of food. Yet glucose is typically higher in concentration inside the cells than in the gut, and therefore transporting it into the cell requires energy. To this end, a glucose-sodium symport harvests the energy stored in the sodium gradient to pump glucose into the cell. According to one model, sodium and glucose can both bind to the pump, but the binding of one makes the binding of the other more effective. When the binding sites of the symport are open to the lumen of the gut, the high sodium concentration makes sodium very likely to bind, and thus glucose will bind more efficiently. Because the conformational change of the transporter will only occur when both sodium and glucose binding sites are filled, both solutes are transported across the membrane in strict unison and are released together into the cell. On the cytosolic side of the membrane, the solutes could, in principle, also bind and thus be exported again by the same route that brought them into the cell. However, while there is plenty of glucose inside the cell, there is very little sodium. Therefore, the binding of both types of solutes only occurs very rarely, such that most of the glucose molecules that enter the cell will not leave by the same route. The import is therefore unidirectional.
We're now going to move on to transport of ions through channels. Focusing on ions, we now need to consider the electrical portion of the electrochemical gradient. So there's a difference in voltage across the cell membrane, right at the cell membrane, that's called the membrane potential. And in this case, the inside of the membrane is usually negative, and this impacts the way ions move across the phospholipid bilayer. This is separate from the chemical gradient, which is simply the difference in concentration. We can see how the gradients can interact. In A, we see that the gradients can combine to produce a greater force than either of them separately. In this case, we have a positively charged ion that has a high concentration outside the cell and low inside the cell, and is also attracted to negative charge at the surface of the membrane. So the chemical gradient, the concentration, is driving the ion to the inside of the cell, and the electrical gradient is also driving the movement of the ion into the cell. In contrast, the gradients can also work in opposition. In this case, the chemical gradient of the positively charged ion would cause the ion to move from the interior of the cell to the exterior of the cell. This is the direction of the concentration gradient. The direction of the electrical gradient would be towards the inside. So the two are in opposition. The chemical gradient, the difference in concentration, drives this ion to move outside the cell, but the negative charge at the surface of the cell membrane attracts those positively charged ions, retaining them within the cell. In this case, the force of the chemical gradient would be greater. This is why we see movement in the direction from inside to outside, but it's a smaller movement than we saw when the forces of the two gradients were combined in the same direction. Ions cannot move across the phospholipid bilayer directly through the phospholipids. They require a channel. Here we focus on the potassium channel and its structure. We can see that it has a central pore, a space that crosses from the exterior of the cell all the way through to the interior, which allows potassium to cross the phospholipid bilayer. There's also something called a selectivity filter that creates the specificity of the channel for potassium and not other positively charged ions. The following animation demonstrates how the structure of the protein creates the selectivity filter.
The bacterial potassium channel is a multi-pass transmembrane protein in the plasma membrane. It is built from 4 identical subunits that are arranged symmetrically. A pore in the center of the protein allows selective passage of potassium ions across the membrane. 4 rigid protein loops, one contributed by each subunit, form a selectivity filter at the narrowest part of the pore. This structure is responsible for the channel's high degree of selectivity for potassium ions over sodium ions. In this selectivity filter, carbonyl groups line the walls of the pore. These carbonyl groups are spaced precisely to interact with an unsolvated potassium ion, balancing the energy required to remove its hydration shell. Passage of a sodium ion through the channel is energetically unfavorable because the sodium is too small for optimal interaction with the carbonyl groups.
Important aspect of ion channels is their ability to open and close. So this ability to switch between a closed shape or conformation and an open shape means that cells can control when ions flow down their gradients, which means there are particular triggers which cause the switch from closed to open conformation. Here are some of the mechanisms used for regulating the opening of ion channels. For voltage-gated channels, the switch or trigger to go from a closed state to an open state is a change in membrane potential. And I'm going to go over membrane potential in just a moment, but you can see there's a switch in the charge distribution. It can be a reversal, like this is showing where you went from positive on the outside and negative in the inside to negative in the inside and positive on the outside, or just a difference in the degree, how much more negative it is on the inside than the outside. So we'll see a change in membrane potential that triggers the opening of those channels. Opening of ion channels can also be regulated by ligands. This can be from extracellular signals, for example, neurotransmitters, which we're going to be looking at here in Chapter 12, or from intracellular signaling molecules, and we'll look at some examples of that in Chapter 16. Mechanical forces can also cause opening of ion channels, and this is common in sensory neurons. For example, in our skin, we have mechanically gated ion channels that are involved in our sense of touch, and in our ears, we have mechanically gated channels that detect the pressure waves caused by sound. So now we're going to begin a focus on ion channels and production of electrical currents in neurons. Therefore, I want to review the properties of a cell's membrane potential. To begin, we can think of a cell as having an equal distribution of charged ions or molecules on either side of the cell membrane, inside and outside. If one type of ion crosses, what results is a difference in charge across the membrane. We see one side is more positive and one side is more negative. There is potential energy in this difference in charge at the membrane. In our cells, it is potassium that creates the membrane potential. To begin, potassium is at a higher concentration inside the cell than outside the cell, and there's no difference in the distribution of charge. So we would say that the membrane potential at this point is 0, no difference in charge, nothing we can measure. There are within cells potassium channels that are called leak channels that can flicker open and closed. When these leak channels open, potassium can leak out of the cell down its concentration gradient. And as potassium is leaking out of the cell, along with it goes positive charge, and the inside of the cell is becoming more and more negative. Eventually, as the interior of the cell becomes more and more negative, there is an attraction between the negative interior of the cell and the positive potassium ions. So at the point when the driving force or the attraction of the potassium to the negative interior is equal to the driving force of the concentration gradient, there will be no net movement of potassium. Any movement of potassium through these leak channels into the cell would be equal to the movement outside the cell. And this sets up a negative resting potential within cells. And this is something we can actually measure the difference in charge from the extracellular fluid to the intracellular fluid. The cell type that we're going to be focusing in these studies is neurons, and neurons produce electrical signals that travel down the axon. We can look a little bit at the anatomy of neurons. It's quite unique. They do have a cell body which looks like your typical cell with a nucleus, but they have these large extensions of membrane near the cell body called dendrites, where messages or signals from other cells are received. So we can see the arrows going in. That's messages that are being received. These messages are processed in the cell body, and if the right conditions are met, the neuron will fire an electrical signal called an action potential. And the action potential can travel down the length of the neuron till we reach the end, the nerve terminals. And this neuron might stimulate another neuron to fire, or maybe do something like stimulate muscle contraction. So we're going to look at this change in membrane potential over time as neurons fire, this thing called an action potential. I'm going to begin by describing the graph we're using. On the x-axis, we're looking at time in milliseconds. And on the y-axis, we're looking at membrane potential in millivolts. An action potential is the process of a neuron firing. Prior to that firing, the neuron is at resting membrane potential, which is set up by the movement of potassium through leak channels. In this case, the interior of the cell is about minus 59 or minus 60 millivolts, more negative than the outside of the cell. So this would be the membrane potential when this neuron is at rest. At this point, both the voltage-gated sodium and the voltage-gated potassium channels are closed. So if I give you the example of a closed sodium channel, there's no open passageway. No ions can pass through. If the neuron receives excitatory signals causing an influx of positively charged ions or a loss of negatively charged ions, membrane potential will become less negative. We can see that happening here where I've marked 2. If this signal decreases the polarity, starts to become more positive and actually hits minus 40, it will trigger an action potential. However, if it does not meet this threshold potential, an action potential will not fire and the neuron will return to resting potential. And there's no action potential happening. So an action potential is often described as an all or nothing. You hit threshold, an action potential is fired. Even if you become more positive, if you don't hit that threshold potential, no action potential is fired. At this point, we have a process called depolarization. When membrane potential hits threshold, voltage-gated sodium channels open. They are tuned to be open at any membrane potential, minus 40 millivolts and above. So here's a picture of the sodium channel. We can see now that it is open, and sodium can pass through the channel, flowing into the cell, bringing positive charge. This causes a rapid increase in membrane potential and reverses the polarity of the neuron so that the interior of the neuron actually becomes more positive than the extracellular fluid. The positive charge that's coming in with the sodium reverses the polarity of the membrane potential. At this peak point, about 42 millivolts, there is another conformational change in the sodium channel where it takes on a shape that's called inactive. The channel is still open because we're above minus 40 millivolts, so we're anywhere above this threshold, but this cork-like aspect of the structure of the sodium channel has flipped over and blocked the channel. At the same time, voltage-gated potassium channels are triggered to open at about the same positive membrane potential, around positive 42 millivolts. Potassium diffuses down its concentration gradient out of the cell. As potassium is leaving the cell, positive charge is leaving the cell, and membrane potential first becomes less positive, then neutral, and then negative again, restoring the polarity of the cell. So altogether, this process of going from resting potential, hitting thresholds, opening voltage-gated sodium channels and having this rapid depolarization, inactivating the sodium channels, opening potassium channels, and having a rapid repolarization, this whole process is called an action potential.